Okay, welcome back everyone. We're going to continue our discussion of potential energy and voltage. And last time we calculated the electric potential from a continuous charge distribution. We did a ring and a disk. And we're going to continue by now looking at the problem of a sphere. And we'll start with a conducting sphere and then move on to insulating. But before we do that, it might be useful to talk for a moment about conductors themselves. So this helps us really understand what's going on with many of these electric potential problems. So a conductor stores all the excess charge on the exterior of the conductor, and it doesn't matter if the conductor is hollow or solid. So if this is my conductor here, keyword being conductor, then all the charge goes to the surface. And this is just something that is true due to Gauss's law. And so that means that the electric field on the inside is 0, and outside it's basically kq over r squared, or total charge q. And the charge will rearrange itself on a neutral conductor in order to cancel out the field. Okay, so if I have a neutral conductor here, and it's placed in an electric field, then what's going to happen to charges in that field? Well, we're going to have if this is a conductor that's neutral, it's going to have charge that's able to move. And in general, what an electric field does is it causes positive charges to move with the field. But in this case, we would have negative charges going this way, leaving behind positive charges here. So here's another example of a conductor. Okay, so I have two charged conductors that are connected by a wire. Okay. So here's sphere A with a diameter of 10 millimeters, so it's a radius of 5 millimeters, and that is connected by a wire to sphere B, which has a radius of 2.5 millimeters. And we want to determine basically how much charge is on A and how much charge is on B, and what's the electric potential of each sphere. So we want VA, VB, QA, and QB. So there's a lot of variables here. Okay, so what do we start with? Well, we start with the fact that if this is a conductor and it's connected by a conducting wire, then VA minus VB is going to be equal to 0. And if that wasn't the case, then charges would be moving around, because remember that definition of voltage is a change in energy per unit charge, and we don't want there to be any difference in potential energy between the two spheres. So the charges are going to move around such that this becomes 0. So that means that basically there's only one voltage that we're looking for, VA, which is equal to VB, which we can just call V. Okay? And we know that V for a charged sphere, because it acts like a point particle, is just kq over r. So that means that VA is equal to VB. And so what we have is that k QA over RA equals k QB over RB. K's cancel, and we get a ratio for the charges that depends on just the radii. Okay, so basically we get QA over 5 is equal to QB over 2.5, or said another way, QA is equal to 2 QB. Now we're also given that it's a total charge of 10 nanocoulombs. So that means that we can also say that QA plus QB is equal to 10. nanocoulombs. Plugging in that QA is 2 times QB, we get basically 3 QB is equal to 10 nanocoulombs, which means that QB is about 3.33 nanocoulombs. And then that means that QA is going to be about 6.67 nanocoulombs, not counting for rounding. Then we can find the electric potential, because the electric potential is just KQ over R. And if you look at this, the ratio of Q over R is the same for each sphere. And that's kind of what happens here, is that the charge will distribute itself so that the electric potential is equal. And it also depends on the radius of the sphere. And if you plug and chug that out, for each sphere, you're going to find about 12,000 volts, regardless of which one you do the calculation for. So that's just one way to set that up. Okay, next example. We want to find the electric potential at a point inside a charged conducting solid sphere of radius r as a function of its distance from the center of the sphere. Okay, so here's our charged conducting solid sphere. But as we said before, all the charge just goes to the surface. Okay, now this tells us two things. First of all, we know that when r is less than big R, we know that E is 0 from Gauss's law, because there's no charge enclosed. But when R is greater than R, we won't worry about the boundary. We'll say when it's equal to R as well. Then we just know that this is KQ over R squared. Okay? Now, if that's true, how do we get to V? Well, remember, V is negative integral of E dot dr. And the way that we want to approach this is that we want to start basically at infinity and work our way in and see what happens as we go sort of inwards against this electric field. So that's where we get our expression, which we just said earlier, for a point particle as KQ over R. But really where this comes from is that when R is greater than or equal to R, V is negative integral of E dot dr, and we're going from infinity to big R at the most. Okay, so that's negative integral, of KQ over R squared dr from infinity to big R. Okay, and so that's going to get us basically KQ over R evaluated from big R to infinity, and that's where we get KQ over big R from. So that's what the potential is as we approach the sphere. But what happens when we're inside? Well, now when R is less than big R, we have the same expression, but we're going to go from basically big R to little r. Okay, wait a second. We are integrating the electric field, which inside of the sphere is 0. So what's the integral of 0? It's just a constant. Okay, so it's a constant. All right, and that means that there's no change in potential as we move inside of the sphere, because there's no electric field. Another way to say this is, if I make some room for a graph here, is that my electric field versus my radius is 0 up until R, and then it jumps up and it's proportional to 1 over R squared. Okay? My potential is any function whose negative derivative will give me E. because remember, let me get a different color here. Remember that, oh, that's not going to show up. Let's do blue. Okay, remember that E is equal to negative dv dr. Okay, so whatever function I pick for v, I have to be able to take the derivative and get my electric field graph. And it turns out that when little r is less than or equal to big R, you have some constant value, and the derivative of a constant is 0. And then we have basically a 1 over r, not a 1 over r squared, but a 1 over r. And the value at big R is the constant value that the potential is throughout. Okay, so the reason that I did this problem first is that now we're going to do the solid sphere. And we'll set this one up. And this one is a little bit of a ride, so buckle up. Okay, so we want the potential at a point inside a charged, non-conducting solid sphere of radius r as a function of its distance from the center of the sphere. Assume that the charge is distributed uniformly. Okay, so first things first, here's our picture. Okay, now this is solid and it's an insulator, which means that there is an electric field inside, and we've solved this problem before. So we're just going to write down what the field is. Okay, so if this thing has a radius of big R, when little r is less than or equal to big R, we have E is equal to, it's going to be, the total charge times little r over 4 pi epsilon naught big R cubed. And that was something that we came up with last time, or in the Gauss's law chapter. Okay, now when r is bigger than big R, so if we're outside of the sphere, remember that it just acts like a point particle, and we have q over 4 pi epsilon naught r squared. And as a reminder, our graph of the electric field versus radius is something that goes up until we hit r. That's that linear function of little r that we're talking about right here, that has the slope that I've circled, linear function of r. And then it's going to decrease as 1 over r squared. So we've seen this before. Now, whatever we do to solve this, we know that our voltage is, or our electric potential, is going to have a graph whose negative derivative is going to be r. So that suggests that we're going to have something of the form negative r squared. Okay? And there's constants in there. And then at some point, presumably at r, it'll switch over to the 1 over r that we saw last time. So this is what we expect to be our result, because E is equal to negative dv dr. Okay, now how do we set this up? Well, we have two things to worry about. Okay, let's say that I have a couple of different points I'm interested in. All right, this question asks us to find the potential inside the sphere, but let's say that I wanted to find it outside at this point B. Okay, well then if I wanted to find it at B, what I would have to do is I would have to find basically that delta V is equal to negative integral of E dot dr going from infinity to B. Okay? And we've seen this before. This is not too bad. Okay? And basically what delta V is in this case is V of infinity minus V of B. Or, sorry, VB minus V infinity. Okay, so that's negative integral from infinity to B of basically KQ over R squared dr. And like we saw previously, that's going to turn into essentially KQ over B. Okay? So nothing too crazy with that. Now, or another way of saying that is Q 4 pi epsilon naught B. Or we could say RB if you want. Okay? All right, now let's say that we want to find the electric potential inside, so point D. Here's where it gets interesting. We're going to set it up, and then we'll do some of the math on another page. So we want to calculate basically VD minus V infinity. So that's going to be, well, we have to do two things. We have to do basically the integral from infinity to R of the electric field when R is greater than big R. Okay, and then we have to minus, okay, the integral from A to little r of E when R is less than big R, less than or equal to. Okay, so now what happens? Well, now we have some fun, because this is going to turn into the negative integral from infinity to R of Q over 4 pi epsilon naught little r squared dr. And then we have a plus sign there. Oh, I'm sorry. Turns out we don't have that second negative sign. I'll come back to that in a second. So it's the integral from big R to, sorry, this should also be big R. From big R to little r of our electric field inside, which is Q little r over 4 pi epsilon naught big R cubed. And that's dr. Okay? So, what does that turn into? Well, that turns into the expression Q over 4 pi epsilon naught R evaluated from infinity to big R minus the expression Q little r squared over 8 pi epsilon naught big R cubed evaluated from big R to little r, or r prime if you want. Okay? We don't want to make the math teachers upset. Okay, and dr prime. Okay, so at this point we're going to switch over to another page real quick and come back to this. And so just to remind you what we had, we're evaluating Q over 4 pi epsilon naught R from infinity to big R, and we're subtracting from that QR squared over 8 pi epsilon naught big R cubed evaluated from big R to little r. Okay, and we don't really care anymore about the limits. So that's going to turn into, essentially for this first term, 2Q over 8 pi epsilon naught big R. Okay, the infinity term will go away. And I can write 2 over 8 because I anticipate the 8 right here. And then I'm going to have to subtract, so QR squared over 8 pi epsilon naught R cubed minus Q big R squared over 8 pi epsilon naught R cubed. Okay, so let's see. Did we do that right? I think so. And then this is going to cancel. And then what we're going to have is essentially, we'll do plus minus plus. You're going to see that we have 3Q over 8 pi epsilon naught R minus QR squared over 8 pi epsilon naught r cubed. Now we're just going to factor out of this a 1 over 8 pi epsilon naught, and then q over big R, and we're going to be left with 3 in that first term minus little r squared over big R squared. And this is our expression for the electric potential, which, if I remind you of our graphs without going back to that other slide, E versus R was linear and then 1 over R squared. Okay, and V versus R, okay, well, so here's big R. This is our expression for R less than big R, okay? And notice that this is, as we predicted, a negative R squared. There it is right here. That's exactly what we predicted would happen. And then once we get to big R, then it turns into the typical 1 over R graph. Okay, so that's pretty cool. And one thing that that we can do to check or to see what else happens here is to plug in when little r is equal to 0, we're going to get V is equal to 3q over 8 pi epsilon naught r. And so that's what this value is right here, and we call that V naught. So V of 0. Okay? And notice that when little r is equal to big R, V is equal to, ready for this, 1 over 8 pi epsilon naught times q over r times 3 minus big R squared over big R squared, which is 1, and OneNote has stopped working. Let's try that again. Okay, well, in any case, what we had was 1 over 8 pi epsilon naught times q over r times 2, because we had 3 minus 1, and that is q over 4 pi epsilon naught r, which is what we expect for the electric potential when little r is equal to big R. Okay, so this took a little bit of time, but I feel like it was important to sort of walk through with you how we calculate electric potential for spheres. Next time, we're going to start talking about capacitance.